Okay, so let's continue with next speaker, Andras Nemethi from Rényi Institute. Thank you.
Thank you very much. So this talk will be about multiplier ideas of normal surface singularities. It's not really it's a little bit different subject, and I apologize for that. But originally, I also planned to speak about some dualities related to singularities, but later I decided to speak about this subject. So, multiplier ideas were introduced in algebraic geometry originally probably by Rickover, and after that was intensively studied by Lazartel, Alain Gustaxes, Piero Bouzour, and it was a very important tool in the study of singularities of algebraic varieties. And usually what actually was important tool in the singularities of divisors. So the ambient space usually was smooth, or with mild singularities, low canonical or terminal, and there was the goal was to study the singularities of divisors, or the global behavior of divisors, and in any dimension can be introduced. So in this talk I will speak about the two-dimensional case, but the ambient space will be an arbitrary normal surface singularity.
Could you multiply with these not introduced by NATO? That
And
was
we also
like
some
1990 or something, or 89. When was that?
I think analytically, yes. And then the algebraic version was.
yes, the definition basically is not very complete.
No, but he has his first application as the vanishing theorem.
So let's fix the what are the objects. So it's I will fix the normal surface singularity. Actually, in this case also I can handle only the complex local analytic case, and I will consider the maximal ideal, the local algebra, and I will consider two different situations. The first, when I will fix an ideal, primary ideal, or I will fix a principal divisor. So function defined on x, and then v is the zero set of that function. And I assume that that has an isolated singularity. And in both situations, I will create a divisor. So that divisor will be important for near local divisor. So I go to the resolution. What is the meaning of the resolution in the case of the ideal? In that case, I assume that the resolution is so good that if I pull back the ideal, then that will be locally feasible, and that is the divisor. In the second case, I pull back, so I consider a good resolution in such a way that the divisor of the function lifted, it's a normal crossing divisor. So these are the two situations, and in both cases, I keep in mind the divisor F. So some terminology about the resolution. So in this is the normal surface singularity. So that means that when I take a resolution, that will be smooth, two-dimensional smooth manifold, and E is the exceptional curve, and the EIs are the irreducible components of the exceptional curve. Associated with the exceptional curves, we can consider also the resolution graph. Everybody knows how the dual resolution graph looks like. Also, these I consider these lattice generated by the EIs. That is actually the second homology of the resolution, and here we have a negative definite intersection form. So that is being non-degenerate. Then over the rationals we can consider the dual lattice. So that is again, it's a free lattice generated of the same rank, but it's a little bit bigger. The R prime divided by L is exactly the homology, the torsion part of the homology of the link of the singularity. What will be important here, I consider the anti-canonical cycle. So actually the dual lattice can be also identified with the cohomology. And that is where the chair class is linked. And the ZK is actually the chair class, the negative of the chair class of the canonical class for the divisor, and that can be computed by a junction formula. So that is basically combinatorics of the resolution graph. So that is really important for us that we have a canonical, anti-canonical cycle in the dual lattice. And just a few words about the terminology. That is in general, in this language is a rational cycle, but if it's an integral cycle, then we call the singularities numerically Gorenstein. Gorenstein means usually that on the regular part you have a never vanishing, nowhere vanishing form. That is an analytic condition. Numerically Gorenstein is a topological or combinatorial condition. It's either that zk is L, or on the regular part, the canonical omega 2, so the canonical line bundle is topologically. And also another important objective with the Lippmann cone, that is the n-time cycles, the cone of n-time cycles. That's also important usually in algebraic geometry, usually the cone of the positive cycles. Here the n-time we need because it's negative definite, so this intersection exactly in this case we will be in the first quadrant, the coefficients are positive. So in that cone we will see that our cycle F is in that cone. And the integral elements of the Lippmann cone are the integral cone and the integral n-time cycle. So this is more or less what we will use. And let's go back. So again, we had a normal surface singularity. Either we fixed an ideal or a principal divisor. In both cases, we go to the resolution and we have a cycle F. And what is the point? That cycle has this good intersection series with the I. So they intersects the suction divisors negatively. So that is in the Lippmann cone. So basically, right now we can forget about the ideal or about the divisor. What is important that we fix this element, non-trivial element in the Lippmann cone. And after that, using that we create the theory, and if we want to solve different cases, ideal or associated with multiplier ideals or with functions, with principal divisors, then we consider the corresponding divisor. So we have a resolution, we have the Lippmann cone, we fix a non-zero element in the Lippmann cone, and we create this cycle. So that means zk plus cf for any c real, and that is the integral part. So that is in the lattice, and that is the LCs of this cycle. So of course that what is happening that when we move c, so we will have bigger and bigger cycles, but because of this integral part, we will have some intervals when it's stable, and after that is a jump. And again, stable and the jump. And again, if we start with say x is smooth, then zk will be integral, and then it's a little bit everything is simpler, but no, technically it's more complicated, this integral part of the cycle. Associated with LC, we could consider an ideal. So that is the ideal of functions, which the pullback of those functions which are vanishing at least with that multiplicity. So that is a tower of ideals. So if we can consider bigger and bigger C values, then we will have smaller and smaller ideals. If C is very, very negative, then basically we get the original ring. At some point we will hit exactly the maximal ideal, and after that smaller and smaller ideals. The point is that all the codimensions are finite, so we can handle these multiplicities, these numbers as invariants of that F. Yes, or an ideal or principal divisor. Yes, so that jumping of numbers, this codimension sequence of codimensions, that is the information what we want to somehow to understand.
Could you go back one slide for the notation? I'm already
Yes.
lost.
Sorry.
Yeah,
Maybe I'm staying in the wrong.
no, it's okay. I'm just.
Yeah. Is it okay? There is any question? So again, we consider for any C, yes, cycle, the corresponding idea, and the sequence of ideas and codimensions. And here is the main definition. So again, if we move C, so we have some jumps of cycles, and then we can consider the corresponding yes, the ideas. And if for some C, for epsilon very, very small, so if for some C jump really happens, then C is called jumping number. Exactly the corresponding multiplicity jump is called a jumping multiplicity. And the difference, yes, of the two cycles, C minus epsilon and C, that is the jumping divisor. Of course, the jumping divisor is combinatorial. So ARC is combinatorial just from the resolution graph in the lattice can be computed. So this is combinatorial, but the jumping of the corresponding jump of the ideal is not necessary. So it can happen that the DC is non-trivial, but we don't see that at the level of ideals. But we might have some functions with fixed so it's that measures exactly the existence of some functions corresponding to some divisors. So that is really a very deep analytic information. On the other hand, we see also here this that the C is periodical, and so then the hope or that the goal is to compute these MCs. So the MCs, then the MC is non-zero, and the corresponding multiplicities, jumping multiplicities for any real, so for all the sequence. So the smallest jumping number, actually, it's combinatory. It's not very complicated because we can consider these numbers. So these are the coefficients of the ZK, the canonical class, and also we have the multiplicities of the divisor M. And it's somehow from that formula of LC, it's almost immediate that these are somehow the candidates, the topological combinatorial candidates, 1 minus Ki over Mi for the jumping numbers, and the very smallest one is actually easy realized, because if we take C smaller, then we will have the big ring. For exactly for this one, we get the maximal ideal. So that is the simplest case that is realized as combinatorial computable. That is somehow threshold in many different ways, appears in algebraic geometry or singularity theory. So that is combinatorial, it's easy to compute. And but in general, the numbers MC are not topological. We will come back to this. Actually, I can tell you right now that, for example, if the ambient singularity is smooth or it's log terminal, then the KIs are less than 1, so this number is positive. Or it's log canonical, then KI might be 1, but it's smaller than or equal to 1. So then the smallest jumping number it's 0 or positive. So that's why in all those cases, only the positive interval was considered. The main point, what I want now to emphasize, or the main message of my talk and this article, is that we hit also the negative part, what is really most challenging. So what was actually not existing before this work. So let's see, first I want to connect the multiplier ideas and then also this jumping number with the multivariable Hilbert function. So for a normal surface singularities, there are two Poincare polynomials, multivariable polynomials or series. One of them is a topological one. Little bit later I will discuss that one. That is computed, it's a zeta function type Poincare series computed from the resolution graph. But this is even more important, which is the analytic, which measures the analytic type of the singularity, which is the Hilbert function associated with the divisorial filtration. So that means that we fix a lattice point, so that is a divisor on the resolution, and we want all those functions which are vanishing at least with that order. And this again filtration of the local ring indexed by the lattice cell, and we consider all the corresponding codimensions. Yes, and this is the Hilbert function. It's a multivariable function, and then we pack everything together, and we get a Hilbert series, and that is somehow it's a very very strong invariant of the analytic type of the singularity. And here it's a typo. Actually, this codimension is exactly h of L of C. If we substitute here L of C, then we recover back exactly the codimension of the multiplier ideas. So basically, M of C in terms of the Hilbert function can be computed in this way.
Could you write the definition of ICF on the whiteboard for people not to fill out?
So yeah, so here
just write it on the whiteboard then.
Yeah, that's a good idea.
Oh, that was
so
yeah.
C is LC is ZK plus CF. Yes, so that is in the lattice. Yes, and then that is from the and then we consider the so we
F is
that is the resolution.
It's a file.
Yes, and then this was the
F is a divisor support.
F is a divisor in the Lippmann cone, so in an L, but basically it's also n times F, so in the Lippmann cone. Yes, then we consider, and associated with this resolution, and then we consider that OX of minus LC, so that is in the local region. So that is all the functions. If I pull back the functions, I pull back, then it has vanishing at least LC. And I want to see if when I move a little bit C, then I can create more functions or less functions with little bit higher multiplicity. Yes. So what is exactly that? Yes. So it's we have the lattice, and then when we move C, then somewhere it's moving up. Yes, the multiplicities, and that we measure the familiar functions. And yes, so in this way, so we're using the Hilbert function. So if we consider now this Hilbert function, so that is L, and we have the Hilbert of L t to the L, that's somehow multivariable if we check everything together. Then from this Hilbert t multivariable series, and then we can recover this, but I want to emphasize that the Hilbert function usually it's very hard to compute. It's analytic, it's very strong invariant, but usually it's very, very hard to compute. On the other hand, exactly this is what I want now to say, that in some cases still computable. For example, when the analytic structure is, when the singularity it has only one analytic structure, for example, the A, the E, or something like that, and then it's easy. Or when it's weighted homogeneous, or when it's very concrete analytic structure, then there is a hope that to compute also the Hilbert function. Well, let's see what is the candidate for it. It's a topological Poincare series. That is purely from the resolution graph. If we have the lattice, then we can consider the dual base elements. Yes, these are some rational cycles with this property. They basically generate also the Lippmann cone. So we consider those ones. So formally, we consider these monomials, yes, and that is the valency of the vertex I. So that is the product corresponding to all the vertices of the resolution graph. And after that, we take the Taylor expansion. So that is a multivariable series, that the exponents are even rational, yes. And that is the point. But what is important, that is from the resolution graph you can compute or you can write. It's very combinatorial, but
May I ask
still.
one question for these Hilbert functions? Are there algorithmic methods to compute those coordinate bases or something?
I don't know. So that really depends on the analytic structure. So you have first to understand all the analytic structures. And that's no hope. Right now, nobody knows what is the moduli space of the analytic structure given on the resolution graph. If it's a topological type, that is resolution graph, see, or the link. But after that, how many analytic structures you have on that topological type, it's unknown. It's very, very even so there's some.
No, I'm saying you fix. I give you one, let's say algebraic.
Oh, you give me equations. Yes,
Yeah,
if you give me the equation.
And then shouldn't there be some coordinate basis method to compute that Hilbert function?
I don't know. I don't know even if Singular has the program Singular has if this is because I don't know if anybody knows a program or algorithm. But maybe I'm wrong. But it's in general, it's. You see, even if you give me, of course, that it's a hypersurface, maybe it's easier, but it's one equation. But even then, I'm not sure that. I don't know, Nero. Do you know any algorithm?
You need to compute first, you need to compute the resolution.
Even the resolution is a problem. Yes, even the topology is a problem. Yes, yes. I'm not sure. So this is a very.
Case, the algorithm, and the ambient smooth case, the algorithm would multiply just for hypersurface plus kilobit rotation modules. There you have.
Yeah, but the smooth ambient space is smooth. Here it's exactly know what time the ambient space it's any analytic type of.
So maybe not.
I am not sure that that is computable by an algorithm. This is okay. That is combinatorially from the resolution graph, that can be computed.
Are there explicit examples of analytic structures on the same topological type,
Yeah,
which are distinguished by Hilbert
Yeah,
function?
that's exactly what I want to say. That this is a topological candidate. That is a topological candidate. If the ring is rational homosphere, then you compute this one, for example, and then so that is the definition of the topological candidate, and this is the theorem that actually how you can go from. It's very interesting. Also, this one. It's not the picture there because I'm so bad in making picture on that. So on the so you have this. 1 minus t to the ei duals kappa I minus 1, and you expand PL, and basically these are no rational, so this will be in the dual lattice t to the L. Yes, here using the character, so you make a choice, so that is p of t, that is z of t, and then you make z0 of t such that those ones which are in the original lattice, so we are integral cycles. This is the choice. Actually, you can make some characters depending of L over this. So make a selection using the Pontryagin dual of this. You separate corresponding to that this series in those classes, and corresponding to the trivial class corresponding to the integral cycles. You have this Poincare combinatorial topological Poincare series. That sits, it's supported on the Lippmann cone. So you have here some elements with some multiplicities. And then the Hilbert function is computed, the h of L, which I told you that it's very hard to compute, that if I want to compute L, the Hilbert of L, then the sum of all the, maybe I'll write down, it's more or less is there, then the Hilbert function of L, Hilbert of L is computed the sum of all the P of, say, L tilde, then L tilde is not bigger than that L. So exactly you consider this zone, this region, that is a finitely, because of the Lippmann cone, is somehow situated in this way in the first quadrant. You consider not greater than L all those elements and make the summation, and this way, that is the candidate, that is the combinatorial topological candidate for the Hilbert function. And what is happening in the case of if it's a link is rational homosphere, then in a lot of cases this is true. Actually, it's true. In this way, you compute the Hilbert function. The Hilbert function equals with this summation if and only if the singularity is price quotient singularity. And that contains all the rational, minimal elliptic, weighted homogeneous singularities. But in some cases, it's very far. It's not the same. So it's not the same. So in those cases, basically MC can be computed. So from the Poincare, from combinatorial Poincare. I don't say that this computation is trivial, technical. So it's combinatorial, very arithmetical. But it's conceptually, in all these cases, MC can be computed. So, for example, even for the smooth case, in this way, there is a way to compute. Okay, so let's go. So I want to discuss now to separate all the discussion in 3 categories: the C positive, C0, and C negative. I told you that when the ambient space is smooth, or the singularities are not very complicated. In the classical case, it was C positive. So that was the classical case. But somehow I want to separate now all these cases, and then maybe I make more emphasis on the C negative case. So again, what I just told that if the ambient space is low terminal or low canonical, then we are in the positive zone. But in general, also the negative zone. I will need 2 more notations. The first is the sheaf homology, that is the geometric genus of the singularity of the X. And that is, of course, that is the more or less is the local Todd index, the analytic Todd index, yes, of the singularity of the surface. And then this is the corresponding Riemann expression. So that is this chi of L is combinatorics, or its topology can be computed. Yes, it's a Chern class, analog of the Chern class, or the, yes, of the, say, analog of the Riemann-Roch formula or Riemann-Roch example formula for the top class. So the PG is analytic index, and chi is the chain class, so the corresponding Riemann-Roch expression for the natural. So let's see the C positive case. So again, LC is this cycle, what I already used, and I use also the jumping, yes, and then that is the integral part, and that is the fractional part. And for C positive, we have that the Hilbert function evaluated in LC actually is not very far from being the combinatorial, but because it's a chi of LC and PG, and that PG is just depends on the ambient space, is C independent. So that is just so that means that if I take the difference, then MC in fact it's combinatorial, it's topological. So for any C positive, we have a very precise formula, combinatorial formula in terms of the Riemann-Roch function for MC, and I can rewrite in a little bit using the definition of chi as a quadratic function, intersection for. But what is important from our discussion, because of the periodicity of the DC, is that this is basically, it's everything is determined more or less, is somehow quasi-periodic. If I know in the interval 0, 1, then it's easily I can compute in also for higher. So the message is that MC is combinatorial, and more or less the focus should be on the first interval, and we have actually, because it's combinatorial, then one should have a very precise formula using the resolution graph. I don't write again that formula. If somebody is interested, I can show you that using the resolution graph, so using the multiplicities of the divisor F and the combinatories of the resolution graph, yes, the Euler numbers, and then yes, the shape of the graph, one can compute the very precise formulas of the multiplicities of the jumping numbers and jumping multiplicities. The C equals 0 case is almost the same, except a little term. So again, the first part is absolutely the same. So chi of L0 plus PG. But when we want to make the difference, then it's a new term appears. And so if we just this wouldn't be there, then would be exactly the same with the periodicity and everything. But that H0 somehow, when we compute M0 appears, and then I want to discuss a little bit that M0. Yeah. So otherwise, it's again we have the same periodicity, and then and combinatorially M star. So I say that is all that number I denote by M star, and M star. So for any positive 0 and positive can be computed combinatorially. But M0, that H0, that correction term, actually it's a sheaf cohomology. It's a very tricky sheaf cohomology. Of course, that ZK is a chair negative of the chair class of KX. Yes. So this is if say if ZK is it's integral cycle, say in the case of Gorenstein, numerical Gorenstein, that this is a bundle with a trivial chain class. But on the other hand, it might be non-trivial bundle. So it depends on the section. So it's so somehow measures how far is from the Gorenstein property in some sense in that zone when the jump happens. And it's actually what is important is it's either 0 or 1. And here it's a precise characterization when it's 0 and when it's 1. You can read it. I can also read it from there or go case by case, but somehow it's analytic. So it depends on the local Picard groups. And if exactly that line bundle is in that corresponding Picard group, it's a 0 element or not, in that case it's 0 or 1. But maybe I give you some examples when it's 0 or 1. So for example, an X is Gorenstein, so that means again that on the regular part I have a non-, so on the regular part the canonical bundle is holomorphically trivial. In that case it's 1, so then that is exactly this bundle is the trivial bundle, so H0 is exactly just the constant functions. If that is non-trivial otherwise, we don't have section, because that's exactly the obstruction to being Gorenstein. So, for example, in the numerical Gorenstein case, or if it's all the exceptional curves are rational, then in the numerical Borenstein case it's 1, otherwise it's 0. In the rational case again, in the AD case it's 1, otherwise it's 0. If the link is integral homology sphere, then again it's 1. But in general, we cannot decide. It really depends on the analytic structure. But again, what is important, I want to go back. Yeah, so well, I want to, yes. So here that otherwise almost everything is like in the positive case, just disappears, and that in that case, for that we have to analyze analytic structure. But otherwise, the zero case is also, it's not, it can be handled. Let's see again just about the first interval, the 0 and 1 interval. I want to do some global statement that if we consider all of them in the first interval, I repeat that somehow in the first interval we have the most important information. Otherwise, it's somehow almost periodical or it can be confused. And if we make the summation over this, then we will have this combinatorial, this topological formula, and this is important in what sense? So this is about the embedded analytic type. So yes, we have we have ambient singularity, and we have also ideal, or we have a divisor there, and we want to understand the ambient analytic information. This is somehow, it's combinatorial, but still it's the ambient somehow. That is how F is situated in the resolution graph. So that is again, it's an ambient, that is the ambient topological type. That's the ambient analytic type, that is the ambient topological type. On the other hand, I want to emphasize the following fact, that if C, its F is given by a function, the principal divisor, and that is isolated singularity, and that is the curve, that is a Cartier divisor, Cartier curve in X, then this chi of minus F actually is the delta invariant of C. And that's a conceptually different. So this is the ambient topological type, or say ambient analytic type, but that is just the abstract analytic type of the curve. So in this sense, this summation is more or less, if we don't regard this, then it's more rational, we don't even have that one, we are being exactly the delta invariant of the abstract curve, which is, it's a good to see that if I have an abstract curve, that how can be embedded in some surface, that is somehow, yes, that is about the embedding, and the surface is about the path, and that is just about the analytic type of the curve. And this also suggests something else, that you see in the case of say, hypersurfaces, plane curve singularities, that we have the Hodge structure, we have the spectrum, Hodge spectrum, that all the spectral numbers in the first interval, if we make the summation of them, that's the delta invariant. That is the summation of MC in the first interval. That is, in that case, the summation of the spectral numbers in the first interval. So there should be a connection. Well, that is the generalization of Nero. So let's see, let's start some preparation for that. So assume that we are in the situation of the function. Here we have an isolated singularity, a holomorphic function defined on an X, and we consider that divisor, and we want to do multiplier ideal associated with F. But let's see from completely different point of view what kind of invariance we can associate with this F. We have the Milnor package. We have the Milnor fiber, monodromy, blah, blah, blah. Yes, we have monodromy operator, eigenvalues of the monodromy operator. They are roots of unity. Yes, that is saying topological or embedded topological invariance. But we have a very strong analytic invariance, the mixo structure. So the cohomology of the Milnor fiber supports mixo structure. Actually, here only H1 is important because of the dimension. So H1 of the Milnor fiber has a mixo structure, and here using the Hodge filtration, we can lift any eigenvalues. So these are the eigenvalues, and yes, these are roots of unity. Alpha is some rational number. Well-defined modulo Z, yes, and how we lift, that lift is given by the Hodge filtration. So if we have the information about that in what Hodge, yes, filtration, in what Hodge group is exactly this corresponding eigenvector, then we can have a lift, and then that is the spectrum. If, of course, that if we want more information, that is the spectral pairs, then we use also the weight filtration, that is the monodromy operator, the nilpotent part of the monodromy operator. But using just the Hodge filtration, we can lift, we have the Hodge spectrum, exactly the number of them, yeah, that should be probably the Milnor number there, but yes. So we have exactly the number of spectral numbers is exactly the Milnor number, so this is exactly the same as this one. Yeah, it's a typo. And what are the more, so in the case of this dimension, x is two-dimensional, all the spectral numbers are in 0, 2, and we have some symmetry. Yes, so that means that again, somehow the information is codified, it's exactly in the first interval. So, and that the Hodge spectral information, we have the first interval, and then if we collect that, then we have exactly, say, the Hodge information of the function f.
That's the only information carried by the mixed Hodge structure.
So numerically, yes, there is also Hodge spectral pairs. When you introduce also, you consider also the nilpotent, the weight filtration. And that the weight filtration is the monodromy weight filtration associated with the nilpotent part.
You need that too.
And basically, numerically, this is the information. So as numerical, of course, that if you consider the variation of then, but as a mixed Hodge structure, say, on the H1 of the Milnor fiber, these are the, of course, that you can study also that how is the Hodge as in the Grassmannian, how it fits the filtration itself. But numerically, these are the numbers. And if you say you don't, the monodromy has no nilpotent part, it's semi-simple, then basically this is it.
If your singularity is not isolated, but maybe say it's
Still you have spectrum, and then you, yes, you can.
say it's compact singularity, compact.
So you would consider the global case.
Well,
Because that is somehow you have here this is Milnor fiber, basically it's in the, it's an object associated by the Derlin factor to the 0.
this is a stock.
Stock, that is basically stock. But of course that you can do also globalize.
If I have that, the dimension of the singular set, is that encoded somewhere in the spectrum? Because that's what Luke was.
So here it's isolated. Even if it's not isolated, you can go to the stock at any point to the singular point, and you can consider the very same one, and that is the Milnor fiber associated at that point. But if you want globally that along a big singular, then again, then you have the limiting structure of the affine or projective. Yes, again you have the So then the ring functor is supported exactly the singular. So what is the theorem? That if first we assume that zk is integral, so for example, if x is smooth, then this is happening, but in many numerical Gorenstein, we have non-smooth case also, so many similarities satisfy this. And for complete intersection Gorenstein, and if x is x, that is the property of x, of the ambient space. And then we consider an isolated singularity, it's a divisor f, and we consider the multiplier ideals in the first interval, in the 0 we just delete that tricky H0, that was 0 or 1, So we consider the multiplier ideals in the first interval, and the theorem is that coincides with the spectral numbers in the first interval of the spectrum. Again, in both cases, the first interval generates almost everything, so basically that is the essential part. That is a generalization of theorem of Nero. He proved it's for the smooth case and in any dimension. So for any hypersurface from Cn to C, he proved that again the multiplier ideas in the first interval and the spectrum in the first interval they coincide. In that case, the spectrum is longer. In the first interval, it's not true that from the first interval you can read the spectrum of everything. But in the first interval, the spectrum and the multiplier the multiplicity, the jumping numbers coincide. And so that is a generalization for any numerically Horenstein case.
That's an Indian mention.
This is again, X is normal surface singularity. That is still its normal surface singularity. And then what is, again, also the left-hand side, also the right-hand side, a priori it's analytic. It's a Hodge and yes, but both can be, I just told that this can be computed from the resolution graph, and also this can be computed from the resolution graph, from the combinatorics of the, and that's a theorem that if X is normal, a plane curve case was a classical, it was computed by Stingray at the school, and but also for X normal surface singularity, and you have a function on it, then from the embedded resolution graph you can compute. If you go in higher dimension, it's very, I don't know how it's, in a very specific hypersurface cases, let's say Newton non-degenerate or weighted homogeneous, then there are formulas for this spectrum. Otherwise it can be, I don't know, no algorithms. I don't know. Yeah. Well, the point is that now if we try, so we have a very precise combinatorial formulas, they coincide, and if we want to apply that one, yes, for here, and then zk is not in the, so we have a combinatorial formula also here, yes, then zk is not integral. In any case, that can be computed. And actually, yes, and this also can be computed, but when the zk is not integral, it's a difference. It's not the same formula. So we have to do something. If we want to generalize this theorem, then for the arbitrary x normal surface singularity, we have to modify. Of course, that I don't want to modify this, because that's the goal that I want to compute that one. So we have to modify the spectrum. How to modify the spectrum? The spectrum was, again, was a function. So there is a page somewhere. Okay, this is the other. Yeah, so I have a function. Yes, I have a function defined on the normal surface singularity, and that has a Milnor fiber, and we have the Milnor package, and that's what we use. Well, what we will modify, we will modify the coefficients of the homology of the Milnor fiber in what coefficients we consider. So this is what is here, it's our C, of the complex numbers. Well, we will generalize that to a mixed Hodge module. So you replace here the homology of the Milnor fiber in the homology of the Milnor fiber in with coefficients in the mixed Hodge module. So that will be that's what we have to do. Of course, that we have to lift everything in the level of mixed Hodge modules. And so no, I don't. The left and right is complicated. It is a Z2 action. It sometimes between these two pages should be. Yes. So here it is. The link is, if the link is rational homogeneous, let's assume then order is few Horenstein. So what is the point? If zk is not integral, that is a canonical class. Then associated with that, you have a representation. Yes, that is, you go to the, or you have a finite covering, that is the regular covering. Yes, and then, or you have a representation, and that gives a mixed Hodge variation on the regular part of the singularity, and just by I lower star, yes, you create a mixed Hodge module on X that is associated with the zk, or with the canonical class of the singularity. And then if everything we repeat with these coefficients in that mixed Hodge module, if we consider the spectrum, then we will have the most general situation that, let's see, X is normal surface singularity. In the left-hand side, we have the multiplier idea of the jumping numbers and the jumping multiplicities in the first interval, and here we have the first interval spectral numbers associated with the mixed Hodge module. So this is say what I wanted to say about C0 and positive. Now we go to the negative case. What I think that it's I repeat, in this case, the positive, except 0 is that the H0 ambiguity, it's computable from the resolution graph. There, I want to convince you that this is a harder case, and really the analytic structure plays an important role. Let's start again with some summation, that if we make the summation of all the numbers, yes, all the jumping numbers on the negative zone, then we have this. This is the geometric genus, that is an analytic invariant of the singularity, and this chi of the, yes, the Chain class of the canonical, the canonical cycle, anti-canonical cycle. If that is integral, then this is basically 0. But it can happen also that PG is 0, those are exactly the rational singularities when PG is 0, then this might be non-zero. So I will give you some examples when this is really non-zero. So even in rational singularity case, this number, actually this is the test, that I have something there or not. And that's a good first try, yes, the negative zone, all of them, and let's see. And for example, if it's numerically Gorenstein, then this is 0, and then exactly PG. If it's rational, then PG is 0, but this can be non-zero. So that is the first sign that how many I expect and how they are there. And also, remember that if not log canonical, then the minimal one actually is in the negative zone. So at least that one is there. So, very good. So let's say an example. This is a rational singularity, even very rational, so minimal rational in the sense of polar, because the weights are sufficiently negative. So here we can actually, the reduced E actually is in the Lippmann cone, so I can consider that one. That corresponds to the generic linear function. And of the maximal generic and the maximal ideal. Yes, and then we consider for that one the multiplier ideal. So we compute this one is rational PG0, but this is n. So we expect n is multiplicities. The very small, the smallest one is 1 minus n, and then the computation tells you that these are exactly that is the n, 1 minus n plus 1, we get 0. These are exactly the jumping numbers, always multiplicity 1. So really, you can have as many as you wish. But here it's an even more interesting example. So I consider this resolution graph. So that is, I have a central fiber, that is a Seifert-Slim manifold. I have an S1 action. Actually, it's we have, yes, it's a S1 fiber over the genus 1 over the torus S1, but we have a one bed fiber, yes, of the S1. Actually, it's a Seifert S1 fiber. Is one Seifert bed fiber, yes, over the elliptic of the torus. And so that is the topological type. So that is the resolution graph of the link, yes. And we consider again this divisor, the simplest divisor is what we have here. But if you consider another one, everything will be different. But for that one, maybe it was easier to compute. And actually, this is an elliptic singularity, and PG is between 1 and 3. That can be by analytic methods one computes these are the possibilities. PG between 1 and 3. So that means that depending on the analytic structure, we have different packages of the multiplier ideas or multiplicities. And so that is what we will have. So we expect 1 or 2 or 3. And actually, it's in this case, if the link is star-shaped, yes, then even we can make a specific analytic structure, weighted homogeneous. When it's Pinkham studied a lot, so it's a good literature about weighted homogeneous singularities. Then we know also something more about analytic structures. So let's consider only those analytic structures which are weighted homogeneous. When you have a C-star action and the local link has a grading, and yes, so it's only weighted homogeneous singularity. It's not hypersurfaces. They are usually, yes, they are not hypersurfaces. Actually, these two are the same one. Usually they are not. So for this graph, we have actually, this is the work of Pinkham, but you can also find other examples, but this was very important for me. He exemplifies some exactly the Pinkham formulas for PG. Actually, that is the Demazur Pinkham Dolbecher formula, if you want to be very precise. So for PG3 is realized by this analytic structure, PG2 is realized by this analytic structure, and if we take something generic, then PG1. Usually when PG is generic, then it's the lowest possible combinatorial bound. And by computation, you see, this should be there because that is the smallest one that is combinatorial, that is from the graph. That should be there. Also, if you remember when we discussed the T0, then in the Gorenstein case, we had T01. So T0 should appear in the hypersurface case. And this is generic that is not Gorenstein, so T0 is not there. And after that, somehow we make the computation, so the only ambiguity is that one, but again, you check that this is the case that you see the topology, even if you have the topology, then the geometry genes can jump, but also this package of the multiplier ideas, multiplicities, might jump, or they are very. So in that way, it's very hard to compute in some sense. And indeed, we really need either the equation or some analytic information. Again, if that hyper singularity is not hyper, it's splice quotient, or somehow we know precisely the analytic type, then there is a hope that you compute for that one. Or even the most generic, for the generic analytic structure, again, should be a combinatorial formula. But otherwise, and even I think that is not so easy. So the generic, in general, we don't really know what is the generic analytic structure. So what is exactly? Okay, so I more or less am at the end. So I want to give you a formula exactly for the arbitrary weighted homogeneous gem. So the splice quotient case, the central node should have genus 0, should be rational homosphere. In that case, we know that it's combinatorial. But for any arbitrary weighted homogeneous singularity, I want to give a formula, and here some terminology, maybe it's not so important. What is important that if you have a weighted homogeneous singularity, you have a cis direction, so the local ring, the local algebra is graded. Yes, so that's the, and then each piece L has finite dimension. So you can consider the analytic Poincare series associated with the cis direction, with the weighted homogeneous structure. Actually, that is related with this one. Here we considered all the divisorial filtration associated with all the divisors. That's multivariate. But if we consider only the divisorial filtration associated with the central, yes, vertex of the star-shaped graph, then we have a divisorial filtration, we have the associated Hilbert function, Poincare, and that is that. So again, this usually it's not combinatorial. It's really on the local ring associated with the cis direction or equivalently with the divisorial filtration. And actually, in the case when G is 0, then PT is topological. That is exactly the Dolbecher-Finkeln-Demazov formula, but usually depends on the analytic structure. And what is the theorem is that using this Poincare by some shift, yes, that is the FIs, and these are some numbers associated with the Seifert, yes, if we can go through it, but somehow the Seifert invariance of the link, they provide some numbers. There's the types of the Seifert S1 orbits, and so that they are well known. So it's a very easy transformation from the analytic, the Poincare series. You recover the complete Poincare of the jumping numbers. And probably this is not a surprise because you cannot have for weighted homogeneous to have two different Poincare. That would be too much, yes. But but still it's not, the proof is not totally trivial. So again, maybe some commons here. So again, you see here there is this shift. So corresponding to C positive here, that is exactly that L should be bigger than some threshold. For those ones that is topological, that is known by some vanishing theorems. And for smaller numbers, that is really depends on the analytic structure. That is, then you don't have the vanishing theorems, and then also suppose that that example, then that is not topological. So for negative zone we have non-topological, for positive zone we have topological, but in all the time can be computed using the Poincare series of the weighted homogeneous of the locally, the Poincare of the locally. So more or less this is what I wanted. So again, C positive is topological, but it's combinatorial computation, and probably that is the challenging part, that in general how to compute, yes, from easily, and how to make interpretations of those multiplicity numbers or jumping numbers or multiplicities. But the real challenge is the negative zone, when it's really about the moduli analytic structures. And so it really can happen that this is a good tool to attack or to try to analyze the moduli space of the analytic structures and what are the invariants and what we can. Of course, that also this is somehow it's a good tool, the Hilbert, the big Hilbert polynomial, but that might be a little bit simpler, and then it has also connection with other parts of mathematics. And so, thank you very much.